And the second thing is the computer power to do this. The microprocessors, they're basically full-blown high-powered computers with wireless built in, with all this cool stuff. And we're talking about a few dollars to put this all together. So the high-tech stuff, although it's really powerful, is not expensive.
So this is really a cost-effective addition, cost-effective addition to your...
Yeah, the basic machine is very simple. It's very simple. The magic is in the electronics. So I read the wind very accurately, and we're talking about, you know, like I said, millisecond, microsecond accuracy of what I'm coming into. And then I go to my computer and I figure out precisely where I want to be a few milliseconds from now. Where do I want that blade? And I have to consider also the rotational momentum of the blade, because I can't stop things instantly. It has to consider all of that momentum. Here's an analogy: it's like a race car that's driving through a course, and he's got to slow down as he comes into the curves, and then he speeds up and races out of the curve, and he really doesn't know what the course is, because I don't know what the course is. The course is constantly changing. And so I can only see a little bit in front of me. And then I basically am racing through this course, controlling the acceleration forces on the rotation of the blade. It's pivoting on its axis as it spins around and going into that optimal position.
And a few questions.
Sure.
How quickly can you really respond to the wind? You were saying that it's so fickle that it changes as far as rotating the blades, and how quickly do they rotate, and how far? How many degrees? How many degrees?
I basically go through a cycle of 20 milliseconds. That's a 50th of a second. And in that 50th of a second, I basically figure out what the status is, and then I send these basically commands to the controller, which is a microprocessor, which sends commands to a driver, which is what controls the current that goes to the coils inside the motor. And then the motor is stepped into the position, and I can control it to within a tenth of a degree. So basically, I send a set of commands for 20 milliseconds. So we're talking about 50 times a second I run through this process, and basically it's a whole new game. A 50th of a second later, I figure out where I'm going to go from there. And as a result, the power is enormous. And not only that, but it is self-starting now. It can start from a dead stop, and it has a positive power contribution immediately.
How did you solve that problem of the self-starting versus the need for power?
The self-starting? Actually, that goes back to your question of how many degrees. When I'm self-starting, the blades are not going fast enough to be airfoils. These are airplane wings, and if an airplane wing is not going very fast, it can't act like an airplane wing. But what I do is I basically turn the thing 90 degrees so it acts as a big plate. And so if you have this blade going like this, straight with the wind, and this one this way, then the wind is just going to push it. So it's just pushing on it. And then so it pushes the next one, this one turns, this one flattens up, and I just push it, and it starts getting up to speed. As it gets up to speed, especially the blades that are coming upwind, start getting more speed, and now they can start acting like airplane wings. And that's you end up with it acting as an airfoil, and it's an airfoil, it gets tremendous lift, and it's that lift that's pulling it forward.
So do the wings have to have different positions relative to the wind, depending upon how fast the wind is going?
Oh, yeah.
So that's really very complicated.
The software is very, very complicated. I'm dealing with air density issues. We've got temperature, humidity, altitude. I've got to know what that is. I've got to understand what the turbulence is. I've got to understand the wind conditions are completely different every time you move it a few degrees. So as the thing moves forward 5 degrees, you're in a new field. Basically, my commands, when we're at high speed, it takes about 20 milliseconds to go about 5 degrees, 10 degrees if it's going really fast. So that's quite a bit, and so you're moving into some new conditions. So 20 milliseconds may sound like a very short period of time, but when you're spinning fast with a strong wind, it's not that much time. And the motor control has to be an accuracy of a couple of millionths of a second.
Seems like your motor would be the weakest link, right?
No, actually these motors are pretty powerful. They're pretty powerful, they're very accurate, and I have absolute control of them. I did the controller myself because there isn't a controller that is made that does what I want it to do. I need to control acceleration. It's not position and velocity. I'm controlling acceleration, torque, and force, and I need to change the rules constantly. And most of these motors, they're made for CNC machines, which are in factories that whip around and make parts.
That's the CNC machine?
Yeah, it'll do drill here and go over here. Well, it wants to go from A to B, and so you have a command for the controller that'll and but I need to control. I don't really know where I'm going. I have to control it constantly, new rules all the time. So I had to do the controller myself. So it's I have just absolute control now. I change the game constantly as it's going. So I have startup conditions. Basically, I turn as a plate, start getting up to speed. It speeds up. I control it. I end up getting power immediately, unlike the normal vertical axis, which needs to be going about 3 times the wind speed, called the TSR, tip speed ratio. You end up getting a net positive power. So you got to be going 3 times the speed. If the wind is blowing 25 miles an hour, the blades have to be going over the ground at about 75 miles an hour before you get any power, net power. Whereas with mine, I'm going right away. And this comes to another thing, a couple more important issues. One of them is the vibration. That as you're spinning, the vibration, there's tremendous forces pulling the center off of the center hub to the left or to the right, back and forth. Huge vibration, huge vibration. And how do you get rid of that? It's intrinsic to the machine. Well, the traditional solution is you just put more mass in the post. That helps. That helps, but there's a lot of force. On my prototype, I have 8-foot blades, and I can have 1,000 pounds of force that's pulling.
8-foot blades are not very long as far as it goes.
8-foot blades, the height of a ceiling. But I can get 1,000 pounds of force that's pulling from the center. It's a lot of force. And so that center wants to move. If you start putting more steel in the hub, you dampen the amount of vibration, but also you have to worry now about harmonic frequencies, where it pulls to left and the right, left, and you end up with it vibrating in harmony, and you end up with constructive interference, where it starts wanting to vibrate more and more, and ends up with more force than you even started with. To deal with that, my tower is a tripod. Just
instead of a single.
Instead of a post. And using a tripod, it's intrinsically stable.
Because there are 3 and not...
Because it comes up to a point, just like a camera tripod, and it ends up very, very stable. It's triangulation and also inexpensive.